Okay, until now, basically we have seen many things, observability, observer, and we applied in a practical way, I would like to say, and we applied or we implemented, better to say, an interesting observer, which is let me say, the first attempt to realize or to implement the observation using observer. The name is Lundberger observer. Lundberger is a professor, an emeritus professor in LA, Los Angeles. I think he's still there. Do you remember I told you this mathematical issues is it's not extremely important in this course, but I try to give you more feeling in order to understand at least what MATLAB does. Just a few words about the nonlinear observability. At this moment is really abstract what I am telling you. I will come back later. We can see in case of if the system is nonlinear means again that I cannot separate causes and effects. This means that states and input, for instance, are somehow mixed together. We will see a little bit in detail when I have the possibility to do an exercise later, no? in the context of nonlinear systems. Nevertheless, the nonlinearity aspect is important because the reality very often is not so linear in the sense, and the linear model is not enough. Now, in the context of the Kalman filter, we will see exactly today, I try to explain that even though the model is not precise, the Kalman filter try nevertheless to find or to estimate the true. About the true, we will speak about later what is the true. But in general, we can see here just shortly that the concept of the observability in nonlinear sense is a little bit more complex. First of all, we have more than one keywords locally. A system is locally observable, the system is observable, the system is locally weak observable, the system is weak observable. Already this allowed me to say that we have to do with something which is extremely complex. I don't now to go in depth on this scheme. I will come back when I will tell you about more in depth what is a nonlinear system. But I would like to emphasize that in nonlinear systems, we speak or we include or we introduce in a new concept which is local. We have also weak, but extremely important the concept of local. This means the observability could be also defined in the local meaning, not everywhere, not for each, let me say, not for all domain of X1 and X2, but for some restriction. We'll come back on this later. But very important, more important, the information of this really abstract slide, and that the test which we can do is not, let me see if I find here, is not anymore sufficient and necessary, but it's just sufficient. This means we will see this test in detail when I introduce an exercise, which is quite complicated at this moment. Forget this. But practically, we will see that it's easy to understand. Practically easy to understand. Very important, the information for today, that's the test, the theorem, is an if condition. This means if something is satisfied, we will see what is something. I can say that the system is locally observable. And then we will see if it's observable, weak, we will see together. But it's just sufficient. This means if the condition is not satisfied, I cannot conclude anything. could be observable, could be not observable. I insist on this because it's a mathematical concept. It's an if. If holds, we can say that it's logically observable. If no, no conclusion. This means it's sufficient. This means if, just if, you have seen that in linear systems, time variant and time invariant, in particular, I insist on time variant, the condition was if and only if. If with 2f, with 2f, means if and only if. This means in both directions. To conclude, this test here is just for this concept here. Locally weak observable. This means at this moment, this definition here remains something theoretical. Okay, now I would like to open the second presentation, and we will start with the Kalman filter. But probably it's worthwhile, even though I told you last time, why Lundberger observer, I can repeat, just repeat, is not enough. Do you remember the last simulation when I introduced the noise? Otherwise, I will do. Do you remember I introduced the noise and the measurements? Noise means errors. I have some corruptions in there, in the data, excuse me. And do you remember the estimation was not so, you remember a lot of spikes in the simulations, in the estimation, simulation, but in the estimation. Moreover, do you remember the calculation, or I derived the Lundberg observer using the hypothesis that I know perfectly the model. A few words I would like to repeat because I see some perplex expressions very shortly. And then this motivates me to move ahead with the Kalman filter, because the Kalman filter tries to manage these two problems. Which one? Noise the measurements. Noise the measurement means something which I don't know exactly the measurements. You remember I told you about the example of COVID. I received the information about the health institution, but they say we're not sure about that. Could be the number of people which is infected is not 100 or 150, between 100 and 150. This means we have some uncertainties in the data, noise in the data. But also the problem could be, now I'll show you, if the model does not reflect exactly the reality. I will be a little bit more concrete on this point using, again, an equation very shortly. Do you remember here? I was able, and now I will repeat again, to obtain this equation here, which is the aerodynamics between what? Do you remember? X minus x hat is the error between what is our true and what I estimate. This is the aerodynamics because it's how it changes the error, the derivative of the error, as a function of a complicated expression, or an expression, let me say. But the assumption here is that A of the representation of my model using A, B, and C, but in particular using A and B, is perfect. I mean, I use the same A and B for the observer, which is this one, and for the system. But of course, this is an assumption. If you remember the stupid example which I presented, the motor for the engineer is clear. I assume that the matrix A is perfectly known. This means I know the resistance of the coil. I know the inductance on the coil. this is basically not necessarily valid as an assumption because it's difficult to estimate or to know parameters. This example here could be also used to understand what I intend. If I built this, you remember, I built this with MATLAB. Now I open MATLAB to repeat. I assumed in the simulation I show you now that -1, which is the true value of the system which I am considering, is exactly -1 also in the model. But could be also -1,1, -1,2, because what I write in the computer in order to describe the reality not necessarily reflect exactly the reality. Now, if these two are hypotheses, no errors in the measurements, no uncertainty in the measurements, and the other hypothesis that I know perfectly the parameters, this means, let me say, roughly speaking, the model. Not necessarily these two hypotheses are valid. Let me open just in 1 second again Lundberg in order to introduce Kalman, what Kalman can do for us. Because last time I implemented the noise. No? Okay, let me open MATLAB. I cannot do that. Let me see if I'm able to open MATLAB from here. From here, I'm sure. Yeah. Then I will share. 1 second. It should appear. Yeah. I think I have to share. No, no, this is not. Where is MATLAB? Ah, okay, excuse me. I didn't see. 1 second again. Yeah, okay. I think you should see the MATLAB. Yeah, what is this? This is different. Rebounded. Something related to our project. Yeah. 1 second. I look for the folder. Yeah, again for MATLAB. No? We have the path because the MATLAB which I have here is basically a window of MATLAB. Now here we can see the path where we are. Probably you know that from Windows. And now I'm looking for the folder where I have the software of last time. This means I don't need to explain what I am doing because this is in a window structure. Let me see if I find quickly now. Here. I think should be here. Let me see if I find. Oh, many things. But it's not here. This means probably. Ah, okay, found it. What I would like to show you, the example was this one. Let me open. Yeah. Look. Let me run. Now let me open the corresponding Simulink file. Let me repeat here the concept. First of all, I would like to tell you about again what happened when I have a noise. So we repeat what I did last time. And we can see, if you remember, that the estimation is not what we have seen without noise. This means practically the observer which I presented until now, this Lundberger observer, at least in this form here, could have some problems to estimate signal, or, measured signal, which with noise. Look what happens. Without, let me share. Okay, let me close this. Without noise, starting from different initial conditions. For instance, I would like to show you just the estimation of the second variable. The Lundberger observer. Yeah. You can see, nevertheless, starting from a different initial conditions, after we discuss a lot, no? We can see that the observer is starting from 0. The real system is starting from -10. But after, I don't know, 0.6 seconds, it seems to be that we are quite satisfied, if we are satisfied. Again, it's an asymptotical observer. I told you about that. I told you. Now, if I have a noise in the measurements, last time we concluded here, if I have a noise in the measurements, look what happens. Noise means the measured data and not exactly the does not reflect the reality. Meaning, the signal here, which is the measured data, are the true data. Again, this is very important concept. This is the real system, characterized by the matrix -1, 1, 0, -1, so something like that. And here the observer. I can manipulate this as I want, but I cannot change this. I mean, I can simulate now, try to imagine what happens using my physical knowledge or an expert about, I don't know, population dynamics, because I'm not expert in population dynamics. I'm not expert in economy. I'm not expert in sustainability. Katharina Benz, if you look, Katharina, did you check Katharina Benz? No, don't do that, but you can do. Gave me the model, because Katharina Benz was expert in the model of this dynamic between fish and fisher. Also, the two students on data science who was expert in internet data gave me the model. And then once I have the model, I can try to build an observer. But this is given. Also, the people who are expert, they cannot say this is the true. This is the model, at least in the simulation. The true is not possible to know. And this is the question which I would like to emphasize. Look now, if the measurements, the data, are affected by error. Independently, if I know or I don't know the model, or the system, better to say. The model, I know, the system. The model reflects the system, or the real system, better to say. Look, of course, we can see that the estimation is not, I mean, could be better. We will see that the Kalman filter can try to manage this problem here. Of course, we can try different variation of Lundberger observer, but the Kalman filter, if you want, is a variation of Lundberger observer. We will see. Now, what happens if the model, which should reflect the system, the real system, is not exactly known? Now we can understand this concept. Let me come back. For instance, this means if I go here, let me share. In order to show you what happens if, for instance, the matrix B with its parameter inside, here the matrix B was, let me show, I think was 0, 1. Let me see quickly. The matrix B, look, what 0, 1? Do you agree? The matrix Z was 0, 1. We can understand, for instance, if you consider the motor, 0, 1 in the motor was the matrix B, the matrix B, which in this case is 0, 1, in the motor was 1 divided L 0. Do you remember? This means if I don't know exactly L, B, the observer, is not B of the system. Now, coming back to this example, this means B, the observer, could be instead of 0, 1, I don't know, let me do an exaggeration. 7, just to show you what happens. Of course, if it's close, we have a nevertheless a difference, but it's not so big. But anyway, a difference, bias. We will see what is the meaning of the bias. This means I have an error in the data. It could happen. Not in the measured data, in the model. Instead of L inductance in our model, 1 millihenry, we have 2 millihenry or 7 millihenry. Here's in a different example, but just to understand that what I am modeling now in the observer is not exactly the system. I don't know if this is clear. And also I can do the same here in the matrix A. Let me show you if now we can see this effect already. It could be that it's very minimal. This means in order to simulate this effect to show you didactically, but not only didactically, I have to write here instead of B, B0, B underscore 0, excuse me, observer. The reason is we have a mismatch between the reality and the model which I use in the observer. The observer consists of a model, not only of the model, consists of a feedback, consists of a matrix L. I don't know if this concept can be understood. One thing is what is. Well, God knows what is. Another thing is what we think that is. Let me see if it's visible, this error. Sometimes for unit problem is not so evident, but could be visible, I hope. Let me simulate now. Let me share. Now here inside, we have a mismatch in the model. Not only, we have also noise here, but let me put more evident what happens if we have an error in the model. This means without error in the data, in the measured data. Let me see if it's evident what happens. Look. Now, of course, I exaggerate with 7, but just to show you that it could happen. Of course, if I write an error of 10%, never tells even a bias. Bias means, you know the word bias, and different. We can see that the estimation now is absolutely not acceptable. Because the real, the true, I can speak about the true. In the simulation, I can speak about the true. Because I know what is, because I create the real model. This is important. In this sense, we can speak about the true and we validate, because this block here, I create from myself, by myself. This means I know what is the truth. Of course, in the real case, then this element here will disappear because I have to consider really the motor, the real motor. Of course, in the engineer fields, we need some element to interface the observer, which is in the microcontroller, with the real system. But this is for the engineer. In the bank, the real system very often is given directly by data, but in any case can be also modeled. But of course, in any case, you have always a mismatch between what is and what we imagine that is. Let me see if I can spend some words more about that. But we can see that if I have an error, of course, if the error is small, we have a small bias, but the bias is there. I will converge asymptotically to a value which is really is not the true value. If I don't have errors, I will converge, of course, asymptotically, but to the true values. If I add also this, of course, now we have some problems. More. Let me see. Because you have bias and also the noise. Okay, now I will open the file of today. And we will see how MATLAB, using MATLAB, not today, but next week, thanks Kalman filter can manage, can try to find a compromise, and can try to obtain an acceptable solution. Okay, let me open the slide the presentation which I uploaded in my study today. Is okay? This velocity of the lecture can a little bit better, no? Also, the repetition it worthwhile sometimes, no? Because last time far away 1 week ago and so on. I will be slowly also more precise on some concepts, I hope. I would like to suggest to redo at home if you have time. The simulation to play with values, with some concepts. And if you have questions anytime, at the end of this lecture, send me an email for a different, I will communicate next week, the office hour, when I am available in my lab to meet all. I will be here next week to meet me also to work together in the context of the examination. But if the schedule is not okay, because I don't know, Sarah, if I am able to do on Friday or Monday, but at the end of the lecture, I'm here. This means we can do ahead as you want. Tell me, then we will arrange another meeting. Also, per Zoom, that can be done. Let me open now. The lecture of today, and let me start with the Kalman filter. We will see many things slowly. Also, the concept of the discrete system. Now I will tell you what I intend. Right? The lectures looks like let me share. No, it's this one. Let me see if I. Yeah. Oh, you're right. Excuse me. Thank you. Let me. I opened the wrong one. Yeah, thank you. This year. Thank you. Now, linear, yeah, thank you for the correction. Discrete. About discrete, do you remember? Until now, we have seen just one picture, one parallel to the continuous. It's not clear what it is. Of course, uh, you have to know that I have a course in master on discrete control and identification. This means, of course, I try to give you some ideas. Really, in master, I have a course. The title is, I don't know if you attended class, discrete identification control. No, I don't. No. Anyway, we have a course on discrete system. This means it's clear it is difficult to understand what I intend, but it's not necessary to understand everything, to have a feeling, because idea is done to implement with the help of MATLAB. Linear, we have a little bit an idea. Discrete, we will see. Kalman filter is exactly the kernel of our topic. Again, as in a state observer. Exactly what I told you at the end of the simulation. I tried to give you some hints and why the Kalman filter is useful for us. Here we have some literature. I already told you about this. I think next week you can also download this introduction and try to read, even though sometimes it's not so easy. I mean, the lecture is enough to understand, in my opinion. But anyway, it's important also to have a reference at least. At the end of the simulation, I told you that basically you have two problems, or the two basic problems. One is related to the knowledge of the system, and another one is related to the error which I have in the measurement. Basically, Kalman filter can help us in both cases. This means it's not necessarily to know perfectly the system. Unknown process state are estimated in an optimal sense. This means we try to find, nevertheless, a compromise. A very important, this sentence here, exact or detailed knowledge of the system is not necessary. We will see that even though I have some errors, I can nevertheless estimate. Very important in an optimal sense. Optimal, I have a course here in master that the title is optimization. Optimal means to find a compromise, to manage, to find a trade-off. Exactly. About the error in the measurements here, I didn't put any specific sentence, but speaking about knowledge, I included indirectly the sentences came from the literature. I included indirectly that I don't know exactly also the system in terms of measurements, in terms of data. This means everything which I don't know can be, it seems to be from this slide, can be managed by the Kalman filter. Because the error in the data affected, nevertheless, the state variables. We have seen also in this simulation, X1 was measured with the noise. Just to give you a feeling. We can see here, nevertheless, in the second sentence, prediction of process states in time discrete process. We will see that the word prediction plays also an important role in the Kalman field. And this can be done, at least in our context, using a discrete system. Look, to introduce a discrete system, we reconsider again this stupid example from my lab, the DC motor, SN motor. Nevertheless, you have here a mathematical representation of the system. I think next time I will show you the bank system. If you don't like, I can show you now. If you don't like, let me conclude this. If I find quickly, I show you the bank. Probably is more intuitive, the bank. Easy. I don't know if it's easier. Anyway, you have a mathematical expression using matrices, using vectors. It's a shame this isn't necessary. This is necessary. At least in the context of MATLAB, matrix laboratory. We can also implement Kalman in different form, but this is the most used, is the easiest form, because the microcontrollers work very directly, I would like to say, with vector and matrices. Anyway, I already told you about this. I already told you about this. I measured the current. It's not the example, this abstract example, x1 derivative equals minus 1 plus x2 is the motor. The concept of the discretization. I have the linear system with its model. Now, we can see in the second part of this slide that I can discretize the system using a particular discretization. The name is forward-Euler discretization. This means question is, can I use different methods? Yes. Which one? We have so many. Please pay attention. When we have many methods, many tools, many observers, many variations, this means no one is good. In the same case, if you have when you are ill, come, I hope no, you go to the hospital and they say, we can apply this, we can apply this, we have many medicaments, or in the pharmacy. You know? Why we have many medicaments? And now it seems a little bit strange what I say, because nobody is good. I can say so. But in my field, I can say so. I mean, in the pharmacy, I don't want to say, just to understand. Could be an answer. Could be an answer. But to be more precise, nobody is good because we have so many different cases that nobody is good for these cases. Not all are good for this case. Better to formulate this in a positive way. This is the same. We have many ways to discretize this equation here. Because depends of many things. What we want to obtain depends how fast is the dynamics. If I have to discretize the bank system, of course, it's not the same if I have to discretize this motor here, in which the variables change over time, something like in order of microseconds. In the bank, the interest does not change. Better to say, the liability, the money which belongs to me is the bank, does not change any microseconds. You sign a contract and the liability change, I don't know, each 3 months. The interest will update it, I don't know, each year, I don't know when. It depends on the contract. This means, of course, the dynamics, how fast change the variables, the state variable, make the difference also in the discretization. Let me go ahead, and then next week I have probably some slide to show you to go more in depth on this. But assuming that the forward-Euler discretization is discretization good for us. What is the forward-Euler discretization? We can see here. I am considering the actual value of the variable, the current, equals the current, which multiply k minus 1 Ts, in which Ts we will see here then with sampling period Ts. I will show you, I will draw you now what is the Ts. the nomenclature very often is without TS, even though it's there, This means IT equal I of k minus 1, in which k is the counter. And the same for omega, the same for u. Very important. What is the derivative? The variation of the current. We can see here, I of k minus I of k minus 1 divided TS. Please keep in mind that inside the argument, we have TS everywhere, because this is just a nomenclature. I show you now what I intend more precisely drawing with the lateral comma. At the end, what is this forward Euler? Assuming TS is fixed. The forward Euler characterizes the actual value with the k minus 1 and the approximation of the derivative in this form here, which is basically the forward element, the future element, minus the actual one divided TS. Let me draw what I intend. So we clarify it, and next week we'll come back on this, because we have to introduce the discrete form of the model to introduce the Kalman filter. Because what I have considered in this course is the discrete form of the Kalman filter. Now we will see, it seems to be complex, but recalling some concept from gymnasium, we will see that it's not it's not extremely difficult to understand what I intend. Why it doesn't work? I know. I think you can see also from home this. Look, I have a variable. I don't know, I of t. No, we call at this moment y of t. Could be liability, could be assets, could be everything which we want to do as a function of the time. Is this the idea? It's easy. Probably you have seen this. This means that I am considering for each k the actual value of the current in this case. Again, please pay attention that theoretically I will do something like that, but in the nomenclature, very often we write without TS, but it's there to save to save blind, to go ahead. In which case, in the counter until infinite. This means for k equal 1, I get this value. For k equal 2, I get this value. And so on. Can you understand? No? Now, what about the derivative? It's difficult here? No. TS is clear what I intend. TS is the difference in terms of time between samples, as I told you. Sample is intuitive. No? I sample. What is the meaning? Meaning, instead of this blue, I will consider this. I will consider this. I will consider this. And we'll consider this, and so on. Yeah, excuse me. Basically, I try to approximate the blue line using the red line, stepwise constant. It's no from gymnasium, I think. I can always do that. Yeah, Tamu, if I make mistake.
The connection between the dots are linear, right?
The connection between dots?
Between two dots from E. Do we approximate that's linear between the 2 points?
The blue line intend? Or this one?
If we want to reconstruct the function and we only have these dots with
Okay.
TS, should we linearize it between?
This is a possibility. Yeah, of course. To do a polygon. Could be. This is exactly the derivative. Based on this, we build the derivative. Based on this, the derivative. I show you what I intend. If you want to reconstruct, we have many possibilities. One is, of course, this, to connect all dots, but not the unique one. It's not the unique one. Of course, could be a possibility. Tamo asked how I can reconstruct the signal. One idea is to connect all dots. Of course, it's an idea, but not the best. You understand what intent is this? Linearly, not you intend. But it's a possible, but not the unique one. We can consider the integral. We can consider weighted integral, many ways to reconstruct. But let me go ahead with this. Forget at this moment to reconstruct. I have a representation, which instead of the blue, I consider the red. Instead of, better to say, I take this point, and the value of this point is valid until the next one, characterized the distance by Ts. What about Ts? About Ts, we will see together. How I can choose Ts. We will see together. At this moment is given. I give you Ts. Also in the project, if it's too difficult for you, I will give you Ts. Sometimes it's given directly from the problem. If this signal represents the liability, you sign a contract with the bank which say, I will give you interest each 3 months. This means TS is fixed by 3 months. Because until 3 months, you don't change anything in bank. Now, of course, change if you withdraw, but not in the sense of the bank, let me say. Of course, in technical, in particular engineering field, TS can be chosen. Very often, also in different system too. But for instance, we worked. I can show you the paper. We worked in the COVID. The data was every day. Basically, every day the health institution says today the infected is something like that. This means the sample time is 1 day. I updated my system. Let me give you just a feeling. Each day, this means TS is 1 day. In electronic fields in a motor, of course, can be chosen because I can sample the signal which appears, or let me say, which are continuous, physically continuous, as I want. In the COVID structure, in the bank, the signals are already for day nature samples. If you sign a contract, each 3 months will be updated. For 3 months, if you don't do anything, it does not change anything. Okay, let me go ahead with this. Because I would like to introduce the camera. I have a few minutes, but I do it. We will come back, nevertheless, also look at the derivative as I introduced before. Now we know this from Gymnasium. But this is just, again, this way here, which is the forward Euler, it's just a way to approximate the function. What is this? This is the future value minus the previous value or the actual value divided Ts. We did a lot of time this in Gymnasium, how we can approximate the derivative, the difference, no? The difference. Now, basically, we don't have the future. In fact, in In some books, we say this is the present and this is the past. But to build mathematically the model, it doesn't matter if this is the present or this is the past. But of course, we don't have the future. Let me come back to the slide and I try to clarify future and present a little bit better. Because the idea now to represent the model. And then we try to interpret what is the future, what is the present. Of course, we don't have the future, but we can predict. Let me show you this concept here, based on a given discretization. Now, we understood a little bit this slide here. Now, if I plug in this position here, this, and the derivative in this model, believe me, don't have to do the calculation. We had at the end this expression and this expression, in which we can see now, independently what I told you, present, the future, that I can use this equation here and this equation here to predict what happens in terms of a current, what happens in terms of velocity, given the previous value of the current, the previous value of the velocity, and the previous value of the input. The same for the velocity. If I show you next week, I will show you the liability of the assets. If this is the liability, I can predict what I will earn at the end of my 3 months. If TS is 3 months, we can see TS appears here in accordance with the contract which I have, considering the model which I have and what I am doing these 3 months. I will try to express a little bit better using the liability model. But in any case, this is the concept of the prediction, which of course, IK is the future. Therefore, I told you is the future, which depends on the present. The present is K-1. I will come back next week. Because what I did is the formal calculation. I didn't do the calculation because I cannot use for the calculation the future. I don't have the future. But in terms of model, we can see that the model in discrete form allows me to see that I can see how we'll earn, I will have at the next step. Could be 3 months, could be 1 month. TS is the step. But of course, it's something related to the technical current and velocity, but also in current and velocity, I can see what happens in the motor. Yeah. Yeah. J is in a particular element in physics, is the inertia. Don't care about it, because you will get an exercise in your context, of course, J. But if you want to do engineering, you are welcome. Is the inertia of the rotor. Next week, I will show you the liability assets. So we can see in a different system. If I find quickly, I will show you also Fish and Fishers, but it's a little bit more advanced because Katarina used this, this project also for her bachelor thesis. Here, we don't have to do the bachelor thesis to pass the exam. You don't have to do publications. The idea is you have to learn a delta, boom. This means the goal is achievable, is reachable. Otherwise, no sense to come here. In life, each goal must be achievable, reachable. Otherwise, let me conclude in a few minutes. Look, I can rewrite everything now in terms of matrices. At this moment, in this case, we have discrete matrices. Discrete matrices. Discrete vectors, or the state vectors. I mean, this information here, I don't want to go in depth. We will see in the exercise by hand. I have already prepared exercise. I rewrote everything which we have in this frame, in these two frames, in terms of matrices and vector. We have seen in the past lecture how I can build row multiply column. Do you remember? Here is the same, but in terms of discrete variables. Very important that on the left, we have everything is in a function of k. On the right, we have everything is a function of k minus 1. When this means the future, if you think that the future is something which depends on the present. This is at the end what I can say. Or if ik is the present, depends on the past. Because if k is the present, k minus 1 is the past. You can interpret as you want. But in any case, it's in a prediction model. Do you remember the keyword prediction model? Extremely important in the Kalman filter. Important concept, observability and in terms of TS. If you look at this picture here, very important, it seems, if I am considering TS smaller and smaller, I have a better approximation. It's clear, no? If TS is smaller, instead of this stepwise representation, for instance, I have something like that, or something like that. If I have a half, excuse me, but you understand what I intend here is wrong. Yeah, we can see. Now, and so on. It's clear, if TS is smaller, you have a better representation, intuitively. Statically, it's true. It's valid, this sentence. But you remember, I told you about the observability. The observability is a dynamical concept because it's related to the differential equations. Here we can see that if TS is very small, theoretically zero, if zero, it seems to be that I fit exactly the blue line. But if TS is small or zero, we have 1 here, 0 here, 0 here, 1 here. If you test now the observability of this pair, do you remember? A, C does not depend on TS. The system is not observable. It is interesting. We have a static, perfect representation, but the system is not observable. I will come back on this. This means TS cannot be extremely small. For the engineers, it's clear that cannot be extremely large, also for not engineer, because if extremely large, the representation is very bad. Let me tell you about that. Just that. This means we have an optimal TS. We have an optimal TS between something which does not realize the observability or is not observable, is something which cannot be accepted as in terms of approximation. Okay, I would like to stop here. Next week we will see in a general possible discretization. I will tell you a little bit also backward Euler in order to show you that exists also different discretization. Matra will be useful for us because we don't do it by hands. Just try to get the concept, and then we will start with the Kalman. Now I will conclude with this. Kalman, we will use discrete matrices, which I rename here with A and B again, but they are discrete. We can see here A equals AK, B equals BK, because AK and BK was exactly what I used here in terms of discrete. One sentence. We can see that the structure of the Kalman consider a new variable of the vector system noise. System noise. Do you remember at the beginning I told you, I come to you, Sarah, I told you not perfect noise on the system, not perfect knowledge on the measurements, without at the beginning distinguish. Now we will distinguish. and what I don't know in terms of system, what I don't know in terms of knowledge. We will see that the Kalman filter is more structured because UXK, UK, A and B, we can have also in the Lundberger. I didn't tell you about the discretization of Lundberger, but it's exactly what I did today. Z is our Y, what in the nomenclature of Kalman is what I am measuring. H is our C, the map of the sensor. But in the Lundberger, we didn't have these new elements, measurement noise, W, which is system noise. What I don't know of the system in terms of model and in terms of measurements, the system. Clara.
You were explaining it, but I want to ask whether the minus dimension is why do you say that, because you don't know at what values are there that are disturbing as for example,
yeah, this is a good question. Is included here. Is included this discretization error is included here. I mean, the system noise, think about what instead of writing 1, I wrote 7. Structural error on the parameters, for instance, or more complex to understand on the order of the system. But keep in mind the parameter. Instead of 1, I have 7. Really something related to the parameter. This error here, which is an error because it's an approximation, this belongs to the measurements because it's related to the signal, is not related to the structure of the model. Therefore, the words measurements noise and system noise, because the parameter is considered an error on the system. And what is related to the signal, also the discretization, is related to the measurements. I will come back. Thank you for this question. Other questions? Okay, this means let me stop to record. I think you see, Anna. Let me see. Should be nice if yeah.
Yes.